Okay, so here we go, warm-up time. Calculate the change in flux. If a 8 centimeter radius circular loop of wire begins perpendicular to an 8 Tesla magnetic field, then tilts 45 degrees to it in 0.2 seconds. So, we're looking for a change in flux, magnetic flux. Remember, anytime you have a change in, you can rewrite it as final minus initial. So, flux, final minus flux, initial. So let's calculate each of these. Flux, in general terms, is B times area times cosine of the angle between them. Okay? So, B times area times cosine of the angle between them. Our initial flux is going to be, let's see, B is the strength of the magnetic field, 8, times A is the area, pi r squared, keeping in mind that r has to be in meters, 0.08 squared, times cosine of the angle between them. We got to be a little careful here. It says the loop itself is perpendicular to the magnetic field, but if you look at the normal vector from the loop, normal vector, and then here's the magnetic field, look, the normal vector lines up. Okay, so our initial angle is 0. So cosine 0, which is just 1. So whatever this mess comes out to be, that's our initial flux. Does anybody have it? We'll calculate it real quick. I'm going to write out the final flux. Flux final. Our magnetic field hasn't changed. Our area hasn't changed. 0.08 squared times cosine. Our angle has changed. Our angle changes to 45 degrees. Okay, so there's our initial and our final flux. Anybody got our initial?
I got
0.169? 1.
1.
Tesla meter squared are the units of flux. Anybody have the second one? Just second entry on your calculator to get that thing back. And then change it to cosine 45. One more, the original by 0.114 Tesla meters squared, which makes sense, right? If we're tilting it, we should be getting a little bit less flux. All right? So from here, let's calculate our change. Final minus initial, 0.114 minus initial, 0.161 gives us stuff. Negative something. Yeah, my brain is on today. 7:37.
0.047.
What?
0.047.
0.047 Tesla meters squared. Okay, so there it is. There's our change in flux. We've decreased our flux by 0.047 Tesla meters squared. Anybody have any questions on that? Easy stuff?
Yeah.
Yeah.
I can just go on screen.
Yes, Mr.
Okay, or off screen. All right, let's try part R. The above loop is then modified to contain 10,000 loops. So I've drawn 1, 2, 3, 4, 5, 6. Okay. 10,000 loops. If the internal resistance of the wire is 3,000 ohms, what current will be produced in the wire? Okay, for this we need Faraday's law. Erase, 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 erase. Erase, erase. I'm going to keep our result over there, the total change in flux. Faraday's law says that EMF, electromotive force, voltage, produced by changing magnetic flux is equal to N times the change in flux over the change in time.
You're changing flux.
Okay? Number of loops times the change in flux over the change in time. Now, lucky us, number of loops is 10, 1, 2, 3.
What's going on?
Change in flux we calculated in part 1. 0.047. Change in time, it says in the problem above, 0.2 seconds, so that's where that piece of information comes in. So what is our EMF?
Can we estimate?
Nope, no estimations.
Well, I say slightly less than 2,500, so we get
Are these cheeses ready, guys?
1,000.
I got 2,050.
2,350
Oh, that's pretty close.
volts.
Yeah.
Okay, is that our answer? Not quite. It's asking for the current. V equals IR. Okay, this is our voltage equals the current times resistance 3,000. So what's our current?
What the?
Let me think about this.
0.78 amps. 0.78 amps is our current. Okay? Anybody have any questions?
Oh, hey. Andrew, give me cheese it.
Andrew's back.
It's like
Okay.
relatively, like, is this as complicated as it's going to get?
Well, the stuff today is a
These
little
two
bit
would not get
confusing.
along.
Yeah,
Yay. Okay,
No, they won't.
erase this stuff.
Because this guy was calling Hans.
So today we're talking about Faraday's law, but more specifically we're talking about another guy, Lenz's law.
We don't have school Friday?
Quick, quick, quick.
Yes! Oh my god, thank god. That
Okay.
made my Monday so much better.
It's only 10 times more than now.
Oh, that's so great. But I have 2 tests this week in physics. That kind of sucks.
Yeah, it is.
I'm hungry.
I'll give you like that.
Okay. So Faraday's law. Let me check it. Make sure I didn't write off the screen here. Yeah, I'm good. Okay, Faraday's law. Electromotive force, EMF, voltage, equals N, the number of loops, times the change in flux over the change in time. This will tell us the magnitude of voltage produced by a changing magnetic flux, right?
Right.
Now, here's the question. What's the direction? Actually, that's kind of weird, because voltage doesn't have a direction, but current does. Okay? If I have a loop of wire, let's say I got a loop of wire like this, okay? And I have a magnetic field going out of the board like this. So that's my B field. Okay? This loop of wire does have a magnetic flux, okay? But let's say this B field is changing, okay? My magnetic field is either getting stronger or getting weaker. That means I have a changing flux, which means I have a changing, electromotive force, okay? So if I have an EMF in this wire, right, it will create a current, okay? But which way does that current go? Does it go around this way, or does it go around this way?
It's gonna go
Does
up.
it depend on the direction of the flux?
It depends on the change in flux, okay?
Why?
Because science.
How does flux influence the current?
Okay, how does it influence current? The way it influences current is actually Lenz's law. Okay, Lenz's law says, okay, and this is kind of confusing wording, so bear with me. Lenz's law says that the direction of the induced current is of that to maintain magnetic flux. Okay? The direction of induced current tries to keep magnetic flux the same. Okay? So, let's say, let's say this B field is decreasing. Okay? So, I've got this loop of wire here, and there's this really strong magnetic field going out of the board. Okay? But it's decreasing. Somebody's turned off my magnet. So it's decreasing, 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 decreasing. Okay? Loop doesn't like that. Loop was happy with his magnetic field. Okay? So what Loop is going to do is create a current that will try and increase that magnetic field again. Okay? How's that going to happen? Well, look at your right-hand rule. I'm trying to increase the flux through the loop. Okay? So if I do the right-hand rule real quick, I can see that that way, okay, going counterclockwise, my magnetic field goes that way, out, through the loop at all points. Like that. Okay? So my induced current will be counterclockwise.
Well, it goes going the opposite direction.
Okay, if the magnetic field was going the opposite direction into the board, and it was decreasing, right?
Yeah.
Then the induced current would want to increase the magnetic field into the board. So I would need it going, this way, the opposite direction, increasing it into the board. Okay, so it would go the opposite way. All right. Similarly, if my magnetic field was increasing, coming out of the board, if it were increasing coming out of the board, okay, so I'm starting here and I'm getting more and more and more and more and more. Well, loop doesn't like that. Loop liked its small original magnetic field, so it's going to try and decrease the magnetic field going through it, okay, and it's going to do that by creating a current the opposite direction, fighting it, okay. So Lenz's law is a little bit confusing, maybe a lot of it. Confusing. Huh?
Okay.
Anybody have any questions?
So the reason we're trying to increase the
Spider-Man's
current.
motorcycle's brakes are weird.
What?
So the reason we're trying to increase the current in the above example is
Or
because.
dimpled?
What do you mean?
It wants to stay in equilibrium.
Basically, yeah.
Yeah, but what direction would the flux be going in the?
Remember, it's not just flux; it's change in flux. If I just put a loop of wire in a magnetic field, just a regular static magnetic field, and just leave it there forever, it will never get a current. It's only when I start changing the flux that I get a current. Okay? Either by changing this magnetic field, or changing the area of this wire, stretching it out or squishing it, or changing the orientation of the wire, like what we did during the warm-ups. Okay? Let's try some more examples. How about this? Let me try and get like a 3D view going on, see if that helps any. This. Get like a loop.
This is a very inefficient motorcycle.
What's wrong with it?
His wind guard is so close to his handlebars, he wouldn't really be able to turn unless he leaned.
Somebody just stopped by our class to throw up some trash. Throw away some trash, not throw up. Okay. Can everybody kind of see the perspective here?
You're trash.
Okay, we
That
got
would be
magnetic-
sorting trash. Just saying.
Magnetic field lines going through a conductor here.
Got it.
Okay? Now, what we're going to do, let's assume this little bar here
Oh, fixed it.
is movable. Okay? This bar here is movable.
You're movable.
I am movable. Okay? Now what we're going to do is we're going to take this bar and move it that way. Okay? So we have a constant magnetic field. We're taking this bar and we're sliding it this way. What is this doing to our loop?
Making it smaller.
It's decreasing the area. So is flux increasing or decreasing?
Decreasing.
It is decreasing. Okay? So we have decreasing area. Thus we have decreasing flux. So the induced current is going to try and increase flux. Okay? The induced current is going to try and increase flux going that way. Which direction would that be? Down here at the bottom. We want more magnetic field going up this way through the current, through the loop.
It would be going to the right.
Thumb would be up here.
It would be going counterclockwise.
The thumb will be going to the right, down here at this bottom part. Look, if I put my thumb on the right, at the bottom part, my fingers curl around and kind of reach behind this little bit right here. Okay? So I get this. Okay? I get the current helping out this magnetic field. Okay?
Wait, so you put your thumb in the direction of the current?
Thumb in the direction of the current, this way. Fingers curl in the direction of the magnetic field, like that. Okay? No matter where I put my thumb, if my current's going the same direction, which it will, that way, and that way. Okay? Now it's going this way, so it kind of curls like that.
Wait, but how do you know the direction of the current?
Well, that's what I'm saying. That's what Lenz's law is. It will always try and keep the flux
I
the same.
understand that, but so originally thumb is direction of magnetic field.
Huh?
Originally thumb is the direction of the.
The thumb was never the direction of the magnetic field.
But
Thumb is always the direction of the charge's motion. Okay, whether it's velocity, if it's a single charge, or if it's current.
but if magnetic field are the fingers, right?
Uh-huh.
Then all you know is it's going right. So couldn't it go right on the top or right on the bottom?
No, if it's going right on the top, this way, then I have magnetic field lines going down into the thing. They're decreasing the flux. I want to increase the flux. I want to do the opposite of this.
Raymond, think of the top view. Think of the top view of this loop. Like what we just did with that. Look at the top view.
That way.
Hey, on a quick side note,
Uh-huh.
can you maybe discuss about, like, on number 12 in our homework, it was talking about how you can tell if it's a south pole or a north pole,
Uh-huh.
depending on the direction of the magnetic field. Can we, like, touch on that
Sure.
again? Okay, cool.
Touch upon.
Yeah. Magnetic field works exactly like electric field. Electric field. So I have like an electric dipole, like a water molecule. Net positive on this side, net negative on this side.
Mhm.
Well, electric field lines always go from positive to negative.
Yeah.
So I get something like that.
So if the magnetic field is going up, it's a south pole? See, and because
But the
that was
problem
their
is
because
it
I looked
just
this up
said that the
online,
magnetic
and
field
they're
is vertical. It
Sorry?
didn't give you specific direction. It said that the wire jumped out, but other than that, there was.
yeah, like number 12, it was just like it's going like the explanation that I found online was like it's going up, therefore
Where's
it
my
must
book?
be a south pole. It's right. Therefore, it must be a south pole. And so I was like, what? Because technically it's going up at the north pole, so it's actually going more up at the north pole.
Let's see, which page is this?
Oh, yeah.
16. Number 12. Force on a wire is maximum that when placed between poles, current flows horizontally to the right. Magnetic field is vertical. So magnetic field is vertical. Wire is observed to jump towards the observer with the currents turned on. What kind of magnetic pole is the top pole face?
Pole position.
So like, I made a diagram, but I don't know if that helped.
Well, yeah. No, it's the
So-
same way. Magnetic field lines always go from north to south.
Yeah.
North to south, north to south. It says the magnetic field is vertical, so it could be going up, it could be going down, okay? But it does say that the current is to the right. B, okay? And then it says that the wire jumps out towards the observer, so you know that the force is out of the page towards you. The only way for that to happen, the only way for force to be towards you is if the magnetic field goes up like that. So you know that this is
Yeah.
not the magnetic field.
Yeah, and I got that part. That's fine.
Okay, so you got that far. Well, magnetic field goes out from north into south. So you know that this guy is north. And you know that this guy south on top.
But it's out of the page, so it goes out from north.
The force is out of the page.
Oh.
So like
Yeah.
your hands like this and
Right. Current, magnetic field lines, force.
What's their curling? Isn't it curling?
Curling is for fields. There's three
But this is a
three.
magnetic field.
Huh?
This is a magnetic field.
No, curling is for magnetic field due to a wire.
This isn't a wire. Just
Uh-uh.
a particle. Oh, just like.
Well, it is a wire, but I mean we're finding the force on the wire.
But the
okay.
magnetic field still would curl. Because it's still a wire. No? Okay. That's stupid.
Now that wire will produce its own magnetic field, and that will curl around.
Oh wait, this magnetic field is like separate.
Yes,
from the
it's
wire?
like a gigantic bar magnet.
So that magnetic field is due to the magnet.
Yes,
Not
not
because
the
of the
wire.
wire. Okay, that makes more sense.
Yeah. Now the wire itself will produce its own magnetic field, and it will go like this. You're right. That
Uh-huh.
will curl around to come out of the page on top, into the page on bottom.
Yeah.
Okay. But there's another magnetic field from the big old bar magnet,
And that's
whatever
what
it
we're
is.
worried about.
Mhm.
That makes sense.
Okay. These are good questions. All right. So back to Lenz's law. Does anybody have any questions about that?
When does the vomit happen with these types of
Completely
problems?
destroyed that poor car.
Oh my god.
If that doesn't work when you put it back together, I'm gonna come after you
Okay, that'll work.
with a knife. Big old butter knife. I'm gonna like
Why
put
do you
it
have a
flat side,
screwdriver
just
with you?
whack it on your head.
Who allowed you to have a screwdriver?
It was on the table and just kind of snapped. Okay, well if nobody has any more questions, let's do some practice problems or some homework problems or something. Bye everybody, have a good luck.